going to do is we're going to use this quiz. I'll provide a link to this from my page. We'll say quadratic residues composite. So we're including in here, we're looking at quadratic residues, but we're not just looking at primes for the modulus. We'll be looking at all numbers, so we could have composites, repeat, we could pretty much any integer for the modulus. And what I'm going to do, we'll have other videos. I haven't posted a video on the Legendre symbol or some of the other background information. So we're just going to go through the problems like I've already covered that, but I'll add videos later and provide links to those so that you can have some more background on this. But some of it, if you haven't seen this before, probably won't make a lot of sense right now. But we're just going to go through the problems and see how it goes. So just going to do basically, I think what we'll do, we'll start at easy though. And we'll just work the problems at random, one at a time. See, say at random, but then I'm going to look for something easy to start with. Actually, it doesn't matter. Let's just go for it. So we have this question. Is 3 a quadratic residue mod 8? And I think what I'll do on this one, we'll just do this one totally manual. Try to give a little bit of background. So what we're looking at is we want to see what's a perfect square mod 8. So I'm just going to list, because 8's a small enough number, I'm going to list all of them out. So 1 squared mod 8 is congruent to 1. 2 squared mod 8 is congruent to 4. 3 squared, I'm going to kind of do like a dot, 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 so I don't have to keep writing that, is 9, but 9 is congruent to 1. 4 squared is congruent to is 16, but 16 mod 8 is 0. Okay. So we get 5 squared. That's going to be 25. 25 mod 8. So the remainder divided by 8 is going to be 1. 6 squared. And this will have a pattern. So 6 squared is going to be 4. 36 divided by 8. The remainder is 4. And last, 7 squared is going to be congruent to 1. So we can see that there's only, we're not really interested in 0. So we're saying we're seeing that the only two quadratic residues mod 8 are 1 and 4. Everything else is a non-residue. Notice I stopped at 7. We only need to check for 8. We only check from 1 to 7. So since 1 and 4 are the only quadratic residues mod 8, then coming back to our question, we're asking, is 3 a quadratic residue mod 8? So that's no, because we only have 1 and 4. So yeah, so that's correct. Okay, so that's one problem down. So let's look at the next one. Is 1 a quadratic residue mod 9? That's going to be very simple. So we're looking for perfect squares in anything that's if the numbers are perfect square in the integers and it's reduced, then it's a perfect square mod 9. So one's going to always be a quadratic residue anyway, but any perfect square, like 4 mod 9. I mean, actually, 4 is always a quadratic residue as well, depending on as long as it's reduced. When I say I say that because let's say if the question was 16, a quadratic residue mod 9, well, 16 is not reduced mod 9, so it wouldn't be. You'd reduce that to 7, and then I believe 7's not. So, but assuming that we're already in a reduced state, which is in this case less than 9, it's a perfect square. So yes. So that was kind of a lot to say for a very simple question. So sorry about that. Okay, we'll keep going. Okay, is 8 a quadratic residue mod 12? Okay, that's interesting. We see that, you know, when I get into a composite number like this, I want to kind of break it up. So let's look at, so 8, get my pen to go. 8 is going to be 2 to the third. And 12 is going to be 2 squared times 3. And then, you know what I'm going to do? I'm going to show in the help, kind of go through all the things you need for these problems, um, including the Euler's criterion, Legendre symbol. But then coming down this where it gets more complicated for our composite numbers. Let's see. So I mentioned reducing. This is composite. So okay, for composite P, you can check the Legendre symbol for each prime factor individually. So let's do that, and let me show you kind of how that goes. So we're looking at the when I say this, we're saying the base P is 12. We're looking at like thought I had my pen working, but it's still not quite doing what I want. Shoot. Okay. So back to 12 is made up of 2 and 3. So what we can do is, I should actually define this. So with the Legendre symbol, we use this notation. And this is basically saying, is A quadratic residue mod P? So it's actually just an abbreviated way of saying this, what we have here. Now, the Legendre symbol is assuming that P is a prime. Okay, but I'm going to use this notation even in these cases. I don't know what people typically do. That's one problem is I'm not sure, but we're going to use that same notation even though we're not necessarily using the Legendre symbol. So in this case, 12 is not prime, but we're still going to look at. So this is not the Legendre symbol, but we're still going to use this notation to say, to be an abbreviation for is 8 a quadratic residue mod 12. So we're using that notation. 12 is not a prime. So then what we're going to do is we're going to look at the primes individually. So what we'll do is we'll look at first, is 8 a quadratic residue mod 2? Now, because 2 divides into 8, this is actually 0. So it's not if you reduce 8, that's 0. So we're going to kind of throw that out. So we have that piece. We kind of like zeros and nothing. So we're gonna go on from there. So then we're gonna check, is 8 a quadratic residue mod 3? And then this can be reduced because 8 mod 3 is actually congruent to 2. The remainder is 2. So this is the same thing as saying, is 2 quadratic residue mod 3? And the answer is no. And for a no, we show a -1. -1 is like, I got a true false setup. -1 is false, 1 is true, and so it's -1. And this actually invalidates the whole thing. So if you break up the prime factorization, and if for any of the primes it's not a residue, then the whole thing's not a residue. So then we can say, is 8 a quadratic residue mod 12? Using this notation, no, -1. The whole thing equates to -1 based on what we found here in our case of 3. So I'll say no. And that's correct. So keep going. I had to back up and get that notation in there. So let's look at another one. Is 5 a quadratic residue on 13? Okay, this is a good one because then 13 is prime. So when we have a prime modulus, then we can use the Legendre symbol. That's the restriction, is we have a good way of calculating primes with the Legendre symbol. So I would say generally what you do is if you have a prime in the base, a single prime, not a multiple prime or anything, just a prime number. And I think it actually not two, so it has to be an odd prime. So if you have an odd prime, then you use the Legendre symbol, and that's simpler. So all we have to do on this one is use Legendre symbol. So let's write that. And then in this case, the notation actually does mean the Legendre symbol. And now what you could do, now when you have a very small number, you could almost just calculate it. But what we want to do is, by the law of quadratic reciprocity, I knew I wouldn't be able to say that, you can flip this. So you can flip it, but you can flip it only, you have to look at each of the mod of mod 4, each of them. So we look at 5 mod 4, that's equivalent to 1. We look at 13 mod 4, that's congruent, I should say congruent to 1. And all we need is either of these to be 1 mod 4. If they're both 3 mod 4, then we have to add a negative sign. But since they're both, or either of them, if either of them are 3 mod 4, we would need to add a negative sign here. But since we have a 1 mod 4, we're not adding anything, so this is fine as it is. And then we can always reduce this, because this is like similar to we were saying now is 13 a quadratic residue mod 5. But if we look at 13 mod 5, that's actually congruent to 3. So we can reduce this to 3 mod 5. And actually what you could do, you could actually just flip this again. Same thing. And we already determined that this is 1 mod 4, so we don't have to add anything. So, but 5 mod 3, I'm kind of doing this the long way because we're kind of starting out, but there's a quicker way to do this that I'll get to later. Oh, I didn't mean to write it that way. But 5 mod 3 is just 2. And then, I mean, really, we could have looked at 5, but when you get to 3, I mean, 3, if you look at the residues mod 3, um, there's only 2 things to check, 1 and 2, because you don't check 3, 3 is 0. So 1 squared mod 3 is 1, and 2 squared mod 3 is also 1. So the only residue mod 3 is 1. So therefore, 2 is not a residue. And that's not the, need that smaller. Fix that. Okay, so we come to -1 there for our answer. So if that's -1, then so it's not a quadratic residue. Ah, I kind of took the long way on that one. I need to speed this up a little bit. Okay, so that's not a quadratic residue. Okay, next one we're looking at is 6 a quadratic residue mod 14. 6 a quadratic residue mod 14. Okay, so what we're going to do, we have a composite mod, so 14 is just 2 times 7. So I think really, so the first step, I think whenever you're composite, really what you want to do first is check each of the prime factors. So 6 is 6 a quadratic residue mod 2, but 6 actually reduces to 0, so we're going to move past that one. and then 6, 7. Well, now we can actually use Legendre symbol on that. And we can actually break this down like this. You can break it down to the factors of the numerator. I call it a numerator. It's not a fraction, but we're calling it the numerator because it looks like the numerator. And we have 2 to the 7, 2, we have 2 over 7 and 3 over 7. And I think what we'll do, I wonder if I have in here the rules for 7. Let's just do something. We'll look at the Legendre symbol quiz. You can also, I'll give a link to this as well. But then in here, we should have some common rules. Oh no, I don't cover 7. I cover 2 though. So for 2, 2 over p is 1 if p is plus or minus mod 8, plus or minus 1 mod 8, and it's negative 1 if it's plus or minus 3 mod 8. So since 7 is actually 7 mod 8 is the same as negative 1. So then this equals 1. But then we'll look at these separately. So 3 over 7, that's actually going to be negative 1, but let's just go through it. So what you can do is quadratic reciprocity, flip it. Both these numbers are 3 mod 4. When both are 3 mod 4, you need to add negative to it. So this is actually negative 1, 1 over 3. We covered previously that 1 over 3, 1 is the only quadratic residue mod 3. So then this piece is 1, and this equates to negative 1. So therefore, we have our 2, 7 is 1, 2 over 7 is 1, 3 over 7 is negative 1. And we can just multiply those like this, and we get negative 1. So therefore, coming back to our quiz, scroll, scroll, scroll. So this is not a quadratic residue mod 14. Good. Okay. Next one, start getting. Oh, you know what I could do? Okay, we'll do this one real quick. I'm actually going to do this one in my head, then we'll move to it. We'll move up a level. So it's for quadratic residue mod 6. Instead of actually checking any of the rules, what we'll do is we'll just say 4 is a perfect square. So because 4 is a perfect square, yes, it's a quadratic residue. So you really don't have to even look at anything when you can recognize that it's a perfect square in the integers, assuming it's reduced. 4 is less than 6, so it's reduced, so that's good. Okay. Move up a level and see something harder. Okay. That's harder. So is 53 a quadratic residue mod 56? And you'll see I actually give the when the numbers get larger, I give a factorization at the bottom just so that you don't have to spend a whole bunch of time factoring each number, which can slow things down. So, okay, so let's write this on the board. So we want to do 53 over 56. Yeah, 53 over 56, sorry. So let's do that. And we know 53 is prime, 56 is 2 cubed times 7. So what we can do, so we'll break it up into the prime so we can look at 53. When you do this, you don't have to look at it 8. You don't have to look at 2 to the third. You can just look at this. We can say is 53 a quadratic residue mod 2. Now, actually, in reality, probably what I'm going to do, I'll stop checking for 2. Because 2, there's nothing to check. Because Let me just show you, like, for an even number, mod 2 convert to 0. This is an even number right here. I don't know if I should use, but yeah. So then if you have an odd number, mod 2, that's 1. But in both cases, those are perfect squares, right? Because 0 squared is 0 and 1 squared is 1. So in the case of 2, you're always getting a quadratic residue. You always have a perfect square. So we don't really have to even look at anything. It's a question of, I mean, it can be 1 or 0, but we're not concerned with that because we're never going to get a -1. We're never going to have a non-residue. So we just can look past checking the 2 case. So then next, we're going to check, is 53 a quadratic residue? Well, it's 7. We can just reduce that. 7 times 7 is 49, so we have a remainder of 4. And we know 4 is a quadratic residue mod 7 because 4 is a perfect square. So that's 1. Okay, so that all checks out. Now, the next thing, we haven't covered this yet, but this check that we did here, breaking up the mod into its primes and checking, like checking the Legendre symbol, or checking if those primes, the prime factorization is quadratic residues. There's another step when we have a power bigger than 1. So this method works if we have, you know, we have 2 times 7 for 14, or it works when you have single primes. But it doesn't work when you have powers greater than 1. So when you have, so in this case, we have 2 to the 3, and so we have more to check. There's more steps here for the larger power. And so let's see. I have here, using the prime factorization, find any repeat factors such as p to the m, blah, blah, blah. And then check for that same prime factorization of a. That's the numerator. So basically, and then for any of these factors, if the power is odd and the power is less than what's in the base, then a is in the. So this is pretty complicated, but let me explain this. And it's actually not too bad in this case. So what we're doing, we have, oops, still struggling with the board. So it's not too bad because 53 is a prime. So let's just write it like this, because what we want to do, yeah, let's kind of look at this. So I write the power, we want to look at the power of 2, as we're interested now in just the 2 part that has a power greater than 1. So let's see, we have like, let's call this power S and this power R. They're saying S equals 0, R equals 3. So 0 is less than 3. So we have to check it, but 0 is even. If we have a odd power there that's less than, so the first check is that it's less than 3. So we have a power less than 3. If it's greater than, we don't have to worry about it. We have power less than 3 and even, so we're fine. If we have an odd power, then we fail it. So okay, the rules at this point get kind of complicated and hard to explain. And the other thing, I kind of went through this on my own. So if someone has a simpler way or a quicker way of getting to the getting through these rules, then let me know. Because I'd like to know it for myself. Because the last part was kind of messy, just going through and defining exactly how it works. But I don't know if there could be a shortcut that I'm missing, just because I couldn't find I mean, I didn't search that hard, but I couldn't find a real good resource to explain a few of these little details at the end. So I just kind of defined it myself. So anyway, the power in the numerator is less than 3 and it's even. So we're good there. But there's one final check here, step 8. If, let me find it. Okay, it's right. If s equals r minus 2, we make one check. If s is less than r minus 2, we do another check. Well, the s is less than r minus 2 is actually, we check that we're 1 mod 8. So let me just sum that up, as that's pretty complicated. But the difference between, so r minus s is 3, which is greater than 2. So when we have a greater difference than 2, we're checking 1 mod 8. And so actually what we're checking, let me just make this, it's actually not that bad when you get to the, when you do it a few times, but it's really hard to explain. We just want to check that. We want to check our numerator mod 8, and it has to be 1. And if you actually divide that out, 8 goes into 53 6 times. That's actually 5. And 5's not going to work. It needs to be 1 at that point. So 5's not 1. So we have to say, let's go back to our original problem. And we'll do more of these, but that is kind of confusing, I think, for people to understand. Say this is -1. It's not a quadratic residue. Almost, but it doesn't meet that 1 mod 8 criteria. Okay, good, we got that. Okay, back to a simpler problem. This should be easier. But now I think when we did this, we did this something like this or really similar the first problem we did. But now we'll do it using some of the rules we know. So we'll look at 3 mod 8. 8 is not a prime. It's 2 to the 3. And so it doesn't want to work. So I just keep saying I'm going to stop checking this, but I keep checking it. So, and I definitely need my pen to work better. So that's not great. Sorry about that. I don't know what I'm doing wrong with the pen. We really don't need to check this because this is always going to be a residue. So checking against 2 is not important. But the interesting to know is this, we have a multiple. We don't have the power of 1 there. So what we want to do is we want to do like we did in the last one. Look at this as 3 times 2 to the 0. And then again, 0 is less than 3, but 3 minus 0 is 3, which is greater than 2. So we need to check it, check if it's 1 mod 8. And 3 mod 8 is not equal to 1 mod 8. It's equal to 3. So this is going to be -1. So that's kind of the long way. You probably need to do that, right? Because this is a pretty easy, this is an easier problem. But I just want to show how that works. This is interesting. So 62 is 62 a quadratic residue? Mod 128. And give us the factorization. 128 is 2 to the 7th. So again, we'll skip the check of the whole, so the whole denominator in quotes is 2. So we're not going to check 62 over 62 quadratic residue mod 2 because it's 0. So we'll go through that part. Then we have 128 is 2 to the 7th, which is a repeat power. So then let's look at the power of 2 in the numerator. So 62 equals 2 times 31. So we have, so I guess maybe let's just kind of do this and look at it this way briefly. So we get a power of 1 in numerator, 7 in the denominator. 1 is less than 7, so we need to check it. But 1 is odd. So if we're less than what's in the denominator and it's odd, then we can stop. That's all we need to know. It can't be a residue if we have an odd exponent in the numerator. So we'll say no, that's not a quadratic residue. I want to get the other case of, yeah, when it does meet the criteria. So is 1 a quadratic residue mod 4? Yes. You know, actually, we could do this the long way. I don't know if I'm kind of beating a dead horse or what, but let's just do it. So we already know it's quadratic residue because 1 is a perfect square, 1's a quadratic residue. But we could look at it. 4 equals 2 squared. So we could write this. Oh, didn't really need that. We could write this as 1 times 2 to the 0 over 2 squared. Then we have our exponents, so 0 is less than 2. So we want to check this. 2 minus 0 is 2. And 2 actually, so if we go all the way down here, we see if s equals r minus 2, so the difference between those exponents is 2, make the following check. And we just need to check that it's 1 mod 4. But it definitely is 1 mod 4. So if we just look at, yeah, I mean, there's not really much, I can write it out, but it's a little over the top because, yeah, that's 1 mod 4. So this whole thing's going to be true, 1. That's just kind of overkill. I don't know if I want to keep doing that or I want to get to the good stuff. Whoa, so this is exactly why I included the prime factorization, because this would be a pain. I mean, this isn't that bad, but I think that would just really slow it down if you had to calculate that. So let's look at this one. $16.92. This is why you need all the tools you can get, because if someone asks you that, it's going to take a little work. So what we want to do is we want to check. So in our numerator, we've got, this is the factorization. So we want to look at 1692. We want to look at it as a quadratic residue mod 3, mod 5, and mod 7. Let's do those one at a time. And so because this is a prime, we can actually use the Legendre symbol. And this is where it helps to know divisibility rules. And what you know is, so if the digit sum, is divisible by 3, then the number is divisible by 3. So what I'm going to do over here, we'll just add up 1 plus 6 plus 9 plus 2 and 18. But 18 is divisible by 3. This is going to be 0. And you can even kind of just group them. Like you can see these are divisible by 3. And 1 plus 2 is 3. So this is divisible by 3. So the good thing is when you break it apart, these aren't that hard to calculate because you can do little tricks like that. Then 1692 over 5. So it's pretty easy. Division by 5 is pretty easy, right? Because we know that it has to either end in 0 or 5. So we know this is the same thing as actually 2 over 5. But that's going to be -1. 2 is not a quadratic residue mod 5. There's what you do basically for 5 is you just kind of, it's good to just know 5, because then you want to reduce to a point where you can actually finish these problems off, so you don't have to string them out and keep checking everything. So like you just look at all the residues, mod 5. It's congruent to 1. This is congruent to 4. But then this is all mod 5. This is also 4. Yeah, the pen doesn't like to do dots very much. And this is 1. So there's only 2 residues mod 4, and it's just 1 and 4. I guess I think I might did one like this earlier and I already forgot. But anyway, that means that 2 and 3 are not residues and -1. And we can stop checking at that point because once you have one fail, the whole thing's going to fail and there's no point to continue on. So this is going to be a no. Okay, we'll do a few more. We're starting to get coverage of everything, but I want to kind of hit all the points. Is 27 a quadratic residue mod 42? Okay, this is different. First thing I want to look at, I mean, it jumps out that 27 is 3 cubed. Let's just write that down so we know that. That could be useful later, maybe. And what is 42? I think 42, okay, 42 is going to be 3 times 7 times 2. All right, so the first thing we want to do is we want to check 27 against each of those. We'll skip 27. We'll skip 27 over 2 case because we know that that's going to be a quadratic residue. But 27 over 3. Well, we said here that 27 is 3 cubes. So this is just going to be 0. 3 divides into 27, so not much to check there. 27 over 7. This is going to reduce to 6. And then I think we did this one before, so that's going to reduce to 6 over 7. But 6 over 7 is going to be 2 over 7, 3 over 7. 7's another good one to get used to because you see it so often that it's better to just start to know it. But we know 2, the rule for 2 is if the mod is plus or minus 1 of 8, then it's 1. So that's going to be 1. And 3 over 7. 3 over 7, you could use the law of quadratic reciprocity and flip it like this. But both of these are 3 mod 4. That's where we get this -1. And then so we end up with -1. This reduces to 1 over 3. And then this is a -1. So we fail at that step. And so once we fail, we stop. And that's just going to be, means the whole thing is not a quadratic residue. Okay. Next one, 22. 22 a quadratic residue mod 36. Okay, so we'll just break up 36. That's going to be 3 squared times 2 squared. So we'll check 22. We won't bother checking 22 versus 2 because, well, I'll just write it out, but that's going to be 1. It's always 1 with 2. But 22 over 3, let's check that. And that's going to be the same as 1. The remainder is going to be 1, so that's just going to be 1. 1's always a quadratic residue. So, okay, so that part checks out. The thing to notice here, though, is we have in the base, we have exponents greater than 1. So we need to break out our numerator. 22 is 2. That's supposed to be a multiplication. 2 times 11. So then we could also write that that's supposed to be a 1. So let's just first check, like let's book that separately. So we have we have to check this power greater than 1, but then we also have to check this one. And in the case of 3, so we have 0 is less than 2, but 0 is even. So we're good there. And for an odd number, we don't have to check anything else. So really our 3 situation is fine because we're 0 is less than 2, and 0 is even. So this is good. This one though is a problem because we have 1 less than 2 and 1's odd. So that's going to fail this. And so 22 is not a quadratic residue. Okay. Maybe just like 2 more. I don't know. I wonder if I have to, maybe I invent I should have one ready. I need to invent one good last problem. Okay, so 137 over 175. And since 175 is composite, we need to check a few things. But this is going to be pretty easy because when we check 137 over 5, this reduces to 2 over 5. And that's just going to be -1. That's not gonna do it. So then that means this is not a quadratic residue. Okay, I think I'm gonna start fishing for something to finish up with. Or we can do some real quick. Like I'm looking at this one and I see this is a power 2, but this is a power 1. So that's gonna be a no. And 11 over 59, that's just a little Legendre symbol. Now let's do that one real quick, because it's a little, I don't think we did a bigger Legendre symbol, so let's do that one. And something like this, what I'll do is I'll just use the law of quadratic reciprocity, flip it. 59 is, I'm freezing. So that's 3 mod 4, and 11 is 3 mod 4. So we need to add a -1 because both those numbers are 3 mod 4 if you do out the division on those. This can be reduced. 11, if you divide 11 into 55, you get remainder of 4. 4 is always a quadratic residue, but we get the -1 in front of it. So this is going to be -1. So this doesn't work. It's not a quadratic residue. Now this looks like a good one, I think. Okay, so 76 is 76 quadratic residue on 128. Okay, 128 is 2 to the 7th. So we can, like I said earlier, we don't need to check 2. So there's no checking this against 2 because we know that's a quadratic residue. We have to go to our rules when we have an exponent of greater than 1. So like let's just do, I don't even know what this notation I'm doing means. I just want to show the exponents together. 2 is less than 7. That's fine. And 2 is even in the numerator. So that's good. We're good there. Then if we do a little subtraction, 7 minus 2 is 5, which is greater than 2. Then going down here to our rules, we want to use our 1 mod 8 case. It's only when the difference is 2 exactly that we use 1 mod 4. Otherwise, we're checking 1 mod 8. And then, okay, so then our last step here, we want to check is 76. We want to check is 76. No, let's cancel that. We want to look at 76 mod 8. And okay, what is that mod 8? That's gonna actually be 4. Oh, I missed one step. Okay, missed one thing. When like you don't have enough to go through here, you need to be we need you to be a lawyer to be able to read through the all the rules. But yeah, there is a little thing in here. So when s is greater than r minus 1, so basically we're talking about this is our r and this is our s. So the difference is greater than 1, right? The difference is 5. Then divide out all factors of 2. So what that means is going back to our numerator, which is we'll write out 76 is 2 squared times 19. What you do basically is you just divide out all those 2's, cancel, you're left with 19. And what we want to check, we don't want to check 76, we want to check 19 mod 8. We check 19 mod 8, and that's 3. And 3 is not equal to 1. So we're very close, but this is not a quadratic residue. So what we can do, I think what we'll do to finish off is we'll do something really similar. I'm just going to tweak this a little because I don't want to keep looking for something that meets my criteria exactly. What we'll finish with is, nope, not 70. Let's look at 68. I think this is going to work. I hope this is going to work. We'll go through this kind of quick because we just did most of the steps. But 68 is 4 times 17, which equals 2 squared times 17. So if we still have the same denominator, so we can look at this. But again, 2 is less than 7. 7 minus 2 is 5. So what we want to do, coming back to where we just were, 2's even, so we're good there. We just want to look at 68 equals, and then we just want to divide out the 4, and we're left with 17. So then what we want to check is 17, what is 17 mod 8? So we're just doing the final check to see that it's 1 mod 8. 17, divide 17 by 8, and you get 1, so it is 1 mod 8. So that actually works. And I don't have the quiz, so let's see just how do we check that. Let's go down here. Let me show you something that you can use when you're doing this. Look at the calculator. So you can use this to kind of check. So we just want to check 68 mod 128, and this should be a quadratic residue. And here we show it right there, 68 over 128 is 1. So we're good. You can do that if you want to play around. I'll put a link to the calculator so you can just try some different values. That's really good for finding some of the more complicated cases and just seeing how it works and playing with it. So that's all I got for now. A lot of questions. And again, I'll post the links, but we'll do other videos to cover separately, like the Legendre symbol, and we'll have the links for a few other related topics.